Hi, how's it going? My name is Carl Diaz with the Learning Resources Center here at the University of Colorado, Denver, and we are going to start the second part of this problem. Like I said in the first one, we can ask this question at once. We can say, hey, you have a styrofoam ball tied with a string at the bottom of a swimming pool or the ocean. What's the tension? You solve that question, and then part B could be you cut the string that's attached to the object. What's the object's initial acceleration? That's the question we're going to solve now. So the initial video that we just did, which is before this one, is solving the tension. Now we're doing the acceleration. So if you didn't watch that one, go watch that one. Or if you watch that one, hopefully you're looking at this one. Now keep in mind from that last one, we said a lot of things. That's why it's important you go watch that video first if you haven't seen that one. Don't watch this one first. Because we said a lot of things that are going to be true over here. Okay, so we know, right, that the buoyant force, a lot of times in terms of representing in fluid dynamics, and it's from the concepts that it's equal to the density of the fluid, volume of the fluid times gravity. We also know that the weight of the object in terms of fluid dynamics, again, it's coming from over here, and that in the video that we solved this, I explain all this. We know the mass of the object, or the weight of the object, can be written like this in terms of fluid dynamics: the density of the object, volume of the object times g. Right, so this is the weight of the object, this is the buoyant force here. The weight of the object can be written this way because we know mass in terms of fluid dynamics should always be written in terms of density times volume, which is just coming from this equation of density, where density is equal to mass over volume. We rearrange this equation for mass, and we see that mass is equal to density times volume. So in all fluid dynamics, we want to take away mass and replace it with density times volume. Okay? If we keep it like this, remember what we said over here. This is statics. Okay? For fluid dynamics, it has to have the densities and volumes, okay? And that's what we're going to go through here. So let me just explain that. Don't forget that stuff, all right? Also, don't forget Archimedes' principle that we talked about over here, that if something's fully submerged, which this ball is going to be fully submerged until it reaches the top, and we're not even talking about when it reaches the top, so it's going to be fully submerged for everything we're talking about. The volume of the fluid displaced is equal to the volume of the object. They're going to be the same, okay? Because of Archimedes' principle, okay? We know that. So when we gotta apply that, when we use that idea, we gotta apply it over here because we can cancel things out, do different things, okay? All right, so just like over here, right, we wanna write a free body diagram. Now again, we're just saying that the string from over here that this object was attached to is cut. So the ball's gonna shoot up because the buoyant force, right, pushes on it. Again, where's the buoyant force coming from? It's coming from the fluid. Why is the buoyant force there? Because the water's made of molecules. The object's made of molecules. Unless those objects mix, those molecules have to make room, or even when they're mixing, I shouldn't say when they're not mixing, but this object's solid, the fluid has to make room for this object. So fluids displace, atoms are displaced. That's where all this idea comes from, and that's where the buoyant force is from, right? The fluid's gonna push, the more the object tries to push the fluid away, the fluid's gonna push back on it, and that's what the buoyant force is. All right, so once we have our free body, because we know our givens, right? We knew that we know the density of the fluid, we know the density of the object and the radius of the object, right? We can write our free body diagram. Now there's no tension; it's not attached to the rope anymore. It was cut. So really, it's the same free body diagram, just without tension. There's buoyant force pushing up because the fluid's always pushing on it, and there's mg, the weight of the object, which is always going to be down. Now acceleration's there, right? It's speeding up, and keep in mind, as this object moves up, the buoyant force changes because the buoyant force has, we can look at buoyant force different ways, but the acceleration is going to change in this object. So we're looking at the initial acceleration here, not the total acceleration. I just want you to keep that in mind. And so, but we also want to include it. So that's the initial acceleration right when we cut the rope, this rope that this object was attached to. But we want it in our free body diagram. And it's also up because that's the way that the styrofoam's speeding up, right? It's going to shoot up and it's going to speed up to the top. All right. All right, so that's our free body diagram. Once we have our free body diagram, just like over here, we want to apply our free body diagram to a Newton law. In this case, we know it's Newton's second law because we know there's acceleration. Now again, we want to label the mass of that object. It's not the mass of the fluid, it's the mass of the object. So there's always we want to label all that stuff up. We explained over here why, but it's important because it could also be the mass of the fluid, right? Okay. So some forces are equal to ma, right, which is the mass of the object times a. If you're curious, like, why? How do you know that's the mass of the object? Because the object is the thing that's accelerating, right? Why would that be the mass of the fluid? The fluid isn't accelerating, the object is. So that's the mass of the object times acceleration, right? Now, when we put in the forces, right, we know buoyant force is positive, and we know weight down is negative. Those are the only forces on the object, and so we know that that part's done. And then we know it's equal, again, to the mass of the object times acceleration, where that acceleration is positive, so that's why that's positive. Remember, it could be negative if it was down, but it's not. All right? Okay. So, what's the first step? Well, just like over here, we look at this equation and say it's not representing fluid statics or dynamics. It doesn't represent a fluid the way I need to talk about fluids. It's representing like solid objects, right? It's looking in, right? So what we want to do is we want to, again, exchange the buoyant force for this. If you don't know why the buoyant force is equal to this, watch the first video, or more important, watch the concept video, because the concept video, it tells you why that is. And when you're watching that concept video, just don't watch it and be like, oh good, the buoyant force is equal to the density of the fluid, volume, fluid times gravity. No, you can replace that in math equations. That's the point of knowing that. It's just not this thing to say or know, okay? So that's what we're doing here. So buoyant force gets replaced by density of fluid, volume of fluid times gravity. Again, it's, if you don't know why, go watch the concept video. There's a reason why we can do that, okay? The weight of the object, right? It gets replaced by this, the density of the object, the volume of the object times g. Again, why? Because m is turning into this. Gravity is just staying put, but m is turning into this. That's why we're getting this equation. Again, trying to represent fluid dynamics. And then m here, right, also gets turned into density of the object times volume of the object. And then that acceleration stays put. So there's a nice equation now. We're like, all right, cool. Now we have an equation that represents fluid dynamics. The other thing that we know is that because of this idea that this thing's fully submerged, so these volumes are the same, that means all these volumes, whether it's the volume of the fluid, volume of the object, right, they're all the same. They're all the same. So why carry them through? That means we can cancel in every term. They're going to cancel, right? And again, why do we know the same? Go watch the concept video or go watch the video before this. But it's Archimedes' principle, okay? That's why we know these volumes are the same. It has to do with submerged objects, okay? So since these volumes are the same, what are we going to do? We're going to go through and cancel these volumes out, okay? And we'll be left with this equation here, right? This is the same equation as this without the volume. So we got the density of the fluid times gravity, density of the object times gravity, density of the object times acceleration, okay? Now, once we get to this point, we can now solve for acceleration. Notice, over here we solve for tension right away, but here I didn't solve for acceleration right away. The reason why is you would have ended up with kind of a funky equation here that you might not have known what to do with. Okay, so here we didn't solve for acceleration. You have to make those choices in physics. And physics isn't just about solving a math problem. It's about solving it in a way that we're going to understand, right? And math is so beautiful that it can work so many different ways that, you know, do it in a way that's going to make sense, right? So here I didn't want to solve for acceleration first. I wanted to cancel my volumes first, pretty much, right? All right, and you won't know to do that until you write it out. So I didn't know to do that until I saw this equation and said, right? Why solve for acceleration here, right? And notice, I didn't try to do it from here. I knew I needed a fluid dynamic equation. Why try to solve for acceleration here? When I got here, I saw what to do. Okay, so for step 2, once the volumes have been canceled out, what we want to do is then solve for acceleration, which is that's what step 2 is doing. So after we solve for acceleration, we get this equation, right, where this density of the object came under the density of the fluid times gravity, right, and then minus this density of the object times gravity. This also came under that, right? I could have brought this underneath and just divided it under all these, but you need to see that this is actually under both terms. The reason why you need to see that this is that density of the object that we bring over underneath these two terms is underneath both terms is because the density of the object right here, right, it's going to cancel. It's going to cancel, and we're going to be left with this equation, right, where just G is going to be left alone here, and here we're going to have the density of the fluid over the density of the object times G, okay? So, once we have this equation, we're pretty much done. We have the density of the fluid, we have the density of the object, we know G, right? We can get acceleration. It's just in physics, we like to make things a little bit prettier. So for step 4, that's all I'm doing. I'm factoring out G. So when I pull G out, all that's going to be left in the parentheses is density of the fluid over the density of the object minus 1. I just want to write that bigger, minus 1. It's equal to acceleration. Okay, that's it. So again, keep in mind the tricks here, because if you don't know that you need to be switching over buoyant force, the density of the fluid, volume of the fluid, you don't know that these volumes are the same, that's why this fluid stuff can get hard. But it's knowing those concepts allows you to do the math, okay? So keep that in mind. That's why you just can't do math here. You gotta know the concepts in order to make an equation that makes sense in order to do the math that we need to do based on the given parameters, all right? So I hope these were helpful. If not, go back and watch and rewatch and go back and watch the concept videos, okay? Remember, it's tied to another video. This question can be asked all together as part A and part B, or it can be asked separate, all right? We'll see you on the next video. Super proud of you.